Hello students, welcome back to the classroom point. In our previous class, we have discussed about the what is oxidation and what is reduction and how to calculate the oxidation number. So in today's class, we shall discuss the type of redox reactions along with the oxidizing agent and reducing agent. So let's begin the class. Oxidizing agent. This is also known as oxidant. So the definition of oxidizing agent is, in a redox reaction, we know that some substances undergo oxidation and some substances undergo the reduction. So oxidizing agent means any substance that oxidizes other substances. Oxidizes other substances by accepting the electrons. By accepting the electrons, and itself it get reduced. Is known as oxidizing agent. So clearly says that it is oxidizing the other substances. It is oxidizing the other substances means it has to take those electrons so that the other substances get oxidized. So by taking those electrons, it is accepting the electrons, and after accepting the electrons, its oxidation number gets reduced. Means itself it get reduced. So any substance that oxidizes other substances by accepting the electrons from those substances and self get reduced is called as the simply oxidizing agent. And let us see the reducing agent. Or it is also known as the reductant. It is exactly opposite to the definition for the oxidizing agent. So reducing agent means it reduces other substances. Reduces other substances by giving the electrons. And itself it get oxidized. So it is reducing them. Reducing means it has to give the electrons to reduce them, because addition of electrons is called the reduction process. So to reduce them, it is giving the electrons, and by losing the electrons itself it gets oxidized. So in case of oxidizing agent, the oxidation number always decreases. In case of the reducing agent, the oxidation number always increases. And let us see what are the examples for the oxidizing agent as well as the reducing agent. Usually, more electronegative elements. More electronegative elements like oxygen and its compound ozone, fluorine, etc. act as oxidizing agents. Similarly here, metals usually act as reducing agents. Let us take some examples to understand these two definitions. So example here is, imagine sodium reacts with chlorine to form NaCl. So in this case, the oxidation state of the elemental sodium is 0. Whereas in NaCl it is +1, and chlorine is 0, and here oxidation number of the Cl is -1. So now here it is clearly says that from elemental form sodium to in compound ionic form Na+, the oxidation number of the sodium increased. That means this process is called the oxidation. And chlorine oxidation number decreased from 0 to -1. So this particular half reaction can be called as the reduction now. So now in this process, who is giving electrons? See, sodium lost electrons and converted into the Na plus form, and later chlorine Cl2 gained those electrons and converted into the Cl minus. So here this is the reduction process and this is the oxidation process. So in this case, sodium is giving, indirectly it is donating the electrons to the chlorine, and sodium makes the chlorine to get reduced. That's why sodium is called as the reducing agent. Whereas chlorine here, chlorine take the electrons from the sodium and itself it get reduced, but by taking the electrons from the sodium, it is responsible for the oxidation of the sodium from 0 to the +1 oxidation state. That is the reason why chlorine is called as the oxidizing agent. Let us take some more examples. Sodium reacts with oxygen to form Na2O. So in this case, oxidation state of the sodium is 0. Here it is +1. Oxidation state of the oxygen is 0. Here it is -2. Then which is oxidized? So we can easily say that the oxidation number of the sodium is increased from 0 to +1, so that it is called the oxidation process, whereas oxygen oxidation state decreased from 0 to -2, so that it is called the reduction process. And in this case, which gets oxidized? Sodium gets oxidized. So that's why sodium is known as the reducing agent. And which gets reduced? Oxygen gets reduced, so that oxygen is called as the oxidant. Let us take another example. Same sodium reacts with the sulfur to form the Na2S, sodium sulfide. Oxidation states 0, 0, +1 and -2. Then we can easily say that oxidation reaction is sodium. Conversion of sodium into Na plus ion is oxidation, and conversion of the sulfur from 0 to -2 is the reduction process. And here oxidizing agent is sulfur. This is oxidant, whereas sodium is reductant. Then if any chemical reaction is given, first of all we have to identify the oxidation state of every element given in the reaction. Afterwards we have to check which compound is get oxidized, that acts as a reducing agent, and which gets reduced, always acting as the oxidizing agent or oxidant. So how to identify whether it is acting as oxidizing agent or reducing agent, or both oxidizing agent as well as reducing agent for any compound? Usually elements exhibits, except S block elements, all S block elements, S block metals. S block metals are always reducing agents. All S block metals always act as reducing agents, but in case of the P block elements and D block elements, most of the P block elements, they act as both oxidizing agent as well as reducing agent. So which compounds acts as oxidizing agents and which compounds acts as the reducing agents? So let us see, if you take any element, the elements may exhibit, in case of the P block, two type of oxidation state, that what we discussed in our previous class. They can exhibit the lower oxidation state and higher oxidation state. So for any element, the lowest oxidation state always act as the reducing agent. Higher oxidation compound always act as the oxidizing agent. And in between lower oxidation state and higher oxidation state, whatever the other possible oxidation states are there, they act as both oxidizing agents and reducing agents. So let's take some examples here. Imagine for nitrogen. Nitrogen exhibits the oxidation states from -3 to +5. And in between many other oxidation states are possible. -2 is possible, -1 possible, 0 possible, +1, +2, +3, +4. All these oxidation states are possible. So in this case here, the highest oxidation state +5 has no other chance to get oxidized. It has only one chance to get reduced. That means whenever nitrogen is present in the form of the +5 oxidation state, it has to accept the electrons to come to any one of these oxidation states. Accepting the electrons means it is acting as a oxidant. And a lower oxidation state, the least possible oxidation state is -3 here for nitrogen. Lower than this is not possible. That means nitrogen cannot accept some more electrons. It has only one chance to lose these electrons and to get oxidized. So that's why it acts as a reducing agent by giving the electrons. What about the compounds that present in these oxidation states for nitrogen? They act as both oxidizing agents as well as reducing agents. For example, if we take HNO2, so in HNO2, nitrogen oxidation state is +3. So nitrogen has chance to go to the +5 oxidation state. Nitrogen has the chance to go to the -3 oxidation state. That means it can get oxidized, at the same time it can get reduced. That's why HNO2 can act as both oxidizing agent as well as reducing agent. Similarly for phosphorus also. Phosphorus also can exhibit the oxidation states ranges from the -3 to the +5. All these possible oxidation states are possible. So -2, -1, 0, +1, +2, +3, +4. So highest oxidation state can act as only oxidant, and least oxidation state, whenever phosphorus is in the form of the least oxidation state, it can act as only reductant. So let us take examples for here. In H3PO3, H3PO4, phosphorus oxidation state is +5. It is always acting as the oxidant. And in PH3, phosphorus oxidation state is -3. So it acts as only reductant. But in between, whatever the other oxidation states are there, so in these possible oxidation state, it can act as both oxidizing agent as well as the reducing agent. For example, if you take H3PO3, where phosphorus oxidation state is 6 + 3, so this is equals to +3. So this one, there is a chance to go to the lower oxidation state and there is a chance to go to the higher oxidation state. And you must remember here one point, that here 0 also there, that we should not forget. Elements in 0 oxidation state, for these elements which are able to exhibit the more than one type of the oxidation states, then they can go to the lesser oxidation state and higher oxidation state. For example, P4 can participate both in the oxidation as well as reduction. Similarly, N2 can participate both in the reduction as well as in the oxidation reaction. Now let us take the chlorine. We know that chlorine can exhibit the -1 oxidation state and 0, +1, +3, +5 and +7 oxidation states. So in the -1 oxidation state, it acts as only reductant. And in +7 oxidation state, it acts as only oxidant. And in between these oxidation states, it can act as both oxidizing agent as well as the reducing agent. So let us take some examples here. ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. So chlorine is exhibiting this type of the oxoacids. So let us try to calculate the oxidation state of the chlorine in this oxoacids. Here it is +1, this is +3, +5 and +7. So chlorine is in its highest oxidation state in the perchlorate ion. So perchlorate ion acts as only oxidant. Here ClO minus can act as the reductant. See, here we are discussing only about the oxoacid ions, not about these oxidation states. So within the oxoacids of the chlorine, this acts as the always reductant. This perchlorate ion always acts as the oxidant. And what about the rest of the cases? Both of these can act as both oxidant and reductant, because for these chlorine has the chance to get either oxidized or reduced. So let us take the question. Find the both oxidant and reductant in the following reaction. So the reaction is given as cuprous oxide react with cuprous sulfide to give copper plus sulfur dioxide. So this is the reaction given. So let's find out which is oxidizing agent, which is reducing agent. And now in this case, the oxidation state of every element, let us find out here. Copper oxidation state is +1, oxygen -2. Here copper +1, sulfur -2. Copper is 0, sulfur +4, oxygen -2. Then which elements gets oxidized and which elements gets reduced? See that oxygen oxidation state, no change. But sulfur oxidation state is increased. So sulfur participates in the oxidation process. Then in both cases copper, from both of these cases, copper oxidation state is reduced to 0. So the oxidation of the sulfur to the +4 is done by the copper, cuprous ions. Cuprous ions took the electrons from the sulfur so that make the sulfur to get oxidized to the +4 and themselves they get reduced to the copper metal. So here, which is the oxidant? Cu1 means cuprous ions oxidize the sulfur so that they are the oxidant. Then which is the reductant here? So reductant is sulfur oxidized and made the copper to reduce. That's why sulfur of Cu2S is the reductant. Now let us see how to find out the stock notations, and these are one type of representations. So stock notations are nothing but just writing the oxidation number of the metal. It is only for the metals, not for the non-metals. So writing the oxidation number of the metals in the parenthesis in a particular molecular formula after the symbol of the metal. That type of representations is called the stock notations. Example, AuCl is there. In AuCl, gold oxidation state is +1, chlorine is -1. That's why here the formula can be written as Au. After the metal, we have to write down the oxidation state of the metal in the Roman number within the parenthesis, and remaining formula has to be written. So that Au1Cl. Now let us take the AuCl3. So that it can be written as Au3Cl3, HgCl2. So mercury oxidation state is 2, Hg2Cl2. Next one, TlCl. So thallium oxidation state is 1, and later chlorine. Anyhow, these stock notations are afterwards discarded. Why? Because after writing of the chemical formula using the oxidation state, it becoming difficult. That's why these are discarded. That's a small part that we discussed here. Now let us discuss about the type of redox reactions. There are many type of redox reactions are there. We shall discuss one by one. So in that, the first category is combination reactions. Combination reactions. So what are the combination reactions? So in the combination reactions, if two substances combine with each other and producing the product is called the combination reactions. And here we have to keep in mind that any one of the reactant must be in the elemental form. If both may be present in the elemental form, but at least one of the reactant molecule in the combination reactions must be in the elemental form, then only it will give the redox reaction. We shall see what happens if the both of the reactants are not in the elemental form but in the combined form, how they are not called the redox reactions. Let us see now. So one of the reactant must be in the elemental form, that we have to keep in mind. So example, H2 plus O2 gives 2H2O. So here both of the reactants are in the elemental form. Hydrogen and oxygen, both oxidation states are 0. Here hydrogen oxidation state +1, oxygen oxidation state is -2. So that hydrogen is oxidized, whereas oxygen is reduced. That's why it is a redox reaction. Now let us see here. Sodium reacts with the chlorine to form the NaCl. So here also we can see that sodium oxidation state is 0, chlorine oxidation state is 0, here +1, here it is -1. Sodium is oxidized, whereas chlorine is reduced. So in these reactions, both of the reactants are in the elemental form. That's why they can be called as the redox reactions. Now let us see what happens if one of the reactant is the compound and other reactant is the element. So it gives CO2 plus 2H2O. So here the oxidation state of this is the compound, this is the element. Elemental form, oxidation state of all atoms equals to 0. Carbon -4, hydrogen +1 oxidation state, carbon +4, oxygen -2, hydrogen +1, oxygen -2. So that you can see that carbon oxidation state increased from -4 to the +4, so that carbon is oxidized. Hydrogen oxidation number no change, but oxygen oxidation state here no change. Here and here both places oxygen oxidation number decreased, so that here and here oxygen gets reduced. Let us see now what happens if both reactants are compounds but not any one of the one is not in the elemental form. For example, CaO plus CO2 gives CaCO3. Here no reactant is in the elemental form, but both reactants are in the compound form. Calcium oxidation state +2, oxygen -2, carbon +4, oxygen -2. Now here calcium +2, carbon +4, oxygen -2. There is no change in the oxidation number of any one of the atom. So this reaction cannot be called as the redox reaction. So one of the reactant must be in the elemental form in the case of the combination reactions. So let us see now second one, decomposition reactions. So what are decomposition reactions? Decomposition means breaking down a molecule or a compound into the smaller molecules or the smaller species is called the decomposition. So in this decomposition is exactly opposite to the combination reactions. So in the decomposition reaction, we will take the one of the compound, we make it to the split into the smaller species, and the products. In that products, at least one of the product must be in the elemental form. Then only such type of the decomposition reactions are called the redox reactions. Let us see here now. Example. Na2O. Imagine it decomposed into sodium plus oxygen. Sodium oxidation state +1. Here it is 0. Oxygen oxidation state -2. Here it is 0. Sodium is reduced. Oxygen is oxidized. So this is a redox reaction. Now let us take 2 KClO3 on decomposition gives 2 KCl plus 3 moles of O2. Then what could be their oxidation states? Potassium oxidation state is +1. Here also potassium oxidation state is +1. Chlorine oxidation state +5. Here chlorine oxidation state -1. Oxygen oxidation state -2. Here oxygen oxidation state is 0. So one of the product is in the elemental form. Now here chlorine oxidation state reduced. So this reduction process, chlorine get reduced, whereas oxygen oxidation state increased from -2 to the 0. So oxygen is oxidized. Let us see now what happens if both products are in the compound form. We shall take the same example. CaCO3 on decomposition gives CaO plus CO2. I had already given the oxidation states of the elements. So this decomposition reaction produces both compounds. No one is in the elemental form. So this cannot be called as the redox reaction, and they are the redox reactions. Let us see the third category of the redox reactions, that is displacement reactions. So what is the meaning of displacement reactions? So displacement reactions means the place of one element is occupied by the another element, that is called the displacement. So let us see here. X reacts with Y and Z. Now X is replacing the Y from its position in the compound of Y and Z and produces XZ plus Y. So if one atom is replaced from its compound by another atom or ion, such type of reactions are called as the displacement reactions. So based on the nature of these atoms that are replaced or that is coming to replace, these displacement reactions are classified into two categories. They are metal displacement reactions and non-metal displacement reactions. Means if metal is replaced by another metal, that is called the metal displacement reactions. So let us see here those reactions. In that first category is metal displacement reactions. So in these metal displacement reactions, one metal replaces other metal ion from its compound. That is what called the metal displacement reaction. Let us see some of the examples. Copper sulfate on reaction with zinc. Zinc replaces the copper from the copper sulfate and produces zinc sulfate and copper. So what information we can extract from this reaction? Oxidation state of the copper in copper sulfate is +2. Sulfur and oxygen all in the sulfate form, here all sulfate form. So sulfate oxidation state directly I am taking as -2. That is no change in the oxidation state of either sulfur or oxygen. Zinc oxidation state in the elemental form is 0. Here it is +2, whereas copper becomes the 0. That means that if you write on the half reactions, so in this case, zinc converted into the Zn2+ by losing 2 electrons. Cu2+ accepted these 2 electrons and converted into the copper. So zinc gets oxidized, whereas copper gets reduced. Apart from this, we can understand one more thing, that the electron transferability. See here, zinc is releasing electrons to the Cu2+ ion and making the Cu2+ ion into the Cu. And here copper is also in contact with the zinc sulfate, but copper is not replacing the zinc. But here zinc replaced the copper ion from the copper sulfate solution. That means here zinc has the more ability to release the electrons than the copper. So electron releasing ability is more for zinc than the copper. And in case of the metals, any metal that has the more electron releasing ability is called as the more active metal. So here zinc is more active than the copper, and by releasing the electrons, these metals reduce the other elements. So more active metals always act as the strong reducing agents. So reducing character as well as the active nature of the metals in this case follow the same order, that is zinc is more than the copper. Let us see the next example. V2O5, vanadium pentoxide, reacts with the calcium to give the calcium oxide plus vanadium. So oxidation states, if you see that vanadium oxidation state is +5, calcium oxidation state is 0. Here calcium oxidation state is +2, vanadium oxidation state is 0. Then which element has the more ability to release the electrons? Calcium is releasing electrons to the vanadium and making the vanadium to convert into the vanadium in the elemental form. So that's 0. So even though both of these are in contact, but vanadium cannot give the electrons to the Ca2+. Why? Because Ca2+ has the more ability, calcium has the more ability to release the electrons than the vanadium. So that here activity series, if you see the activity, which metal has the more active nature, calcium has the more active nature than the vanadium. At the same time, calcium is the better reducing agent than the vanadium. TiCl4 plus 2 moles of the magnesium gives 2 MgCl2 plus titanium. So in this case, titanium oxidation state +4, magnesium oxidation state 0. Here magnesium oxidation state 2 plus and titanium is equals to 0. So electron releasing ability is more for the magnesium than the titanium. At the same time, magnesium is better reducing agent than the titanium, and magnesium is a more active metal than the titanium. Cr2O3 plus 2 moles of aluminum converts into the Al2O3 plus 2 chromium. Here oxidation states, if we assign, chromium oxidation state is +3, aluminum 0. Here aluminum +3, chromium is 0. So which metal is more active? Aluminum is more active than the chromium. So that is the reason why aluminum is acting as a reducing agent for the chromium oxide to convert the chromium oxide into the elemental chromium. Let us see the non-metal displacement reactions now. In these non-metal displacement reactions, usually non-metal is replaced. Means non-metal is removed from its compound. Usually that non-metal could be hydrogen in most of the cases, and some cases it is oxygen, and some cases halogens. Except fluorine. So remaining cases, so that you can see that hydrogen, oxygen and some halogens. So let us see here, this non-metal, whether it is replaced by the metal or other non-metal. So based on this, again these reactions are classified in two categories. That is non-metal displaced by the metal and non-metal displaced by the non-metal. So let us see here, first one, non-metal displaced by metal. Non-metal displaced by metal. So in these reactions, we can see that activity of the metals. All alkali metals. All alkali metals replaces H2 from water. All alkali metals. So if you take this sodium reacts with H2O to form sodium hydroxide and replaces the hydrogen in the form of hydrogen gas from the H2O. And some alkaline earth metals like calcium, strontium, barium. So only these three alkaline earth metals can react with cold water. So these are more active metals. For example, if you take the calcium and H2O, it gives calcium hydroxide and liberates the hydrogen gas. And what about the other alkaline earth metals? So beryllium, only magnesium is left behind. Beryllium is a non-metal. So here beryllium, what about in the case of the magnesium? Magnesium and other some inactive metals or some less reactive metals do not react with cold water but with steam. They react with the steam. So magnesium with H2O, it gives magnesium hydroxide plus hydrogen gas is released. Similarly, let us take the iron. Iron is also a less active metal. Iron on reaction with the steam, it forms Fe2O3 and liberates the hydrogen gas. So they need some amount of the energy to react with the water. Cold water they don't react, but they react with the steam. And what about the other metals? Not about only these metals. There are some metals which don't react even with the steam or cold water, but still react with the acid and liberate the hydrogen gas. So let us take here, zinc reacts with HCl to form ZnCl2 and liberate the hydrogen gas. Similarly, magnesium also you can take. Magnesium react with the HCl to form the magnesium chloride and liberate the hydrogen gas. What about iron? Iron on reaction with the hydrogen chloride, it forms FeCl2, not FeCl3, remember that. So forms the hydrogen gas. Similarly, cadmium and tin also react with the acids and liberate the hydrogen gas. So these are the non-metal displacement by the another metal. Let us see what if non-metal is displaced by another non-metal or not. Non-metal displacement by non-metal. Both are non-metals only in this case. Let us take first of all with the fluorine. Fluorine on reaction with the water, it can oxidize the water into the oxygen gas. That is the reason why fluorine reactions cannot be conducted in the aqueous medium. Why? Because if water is available, automatically fluorine oxidizes the water into the oxygen gas, so that water cannot be available as a medium. That's why fluorine reactions cannot be carried out in the aqueous medium. Now let us see here. Oxidizing nature of halogens is fluorine is greater than chlorine, is greater than bromine, is greater than the iodine. So what information we can gather from this order? That means higher oxidizing halogen can oxidize the halide ion of the lower oxidizing agent into its respective halogen. So here we shall see here. You take the fluorine, chlorine, bromine and iodine. Let us take the respective ion salts F minus, Cl minus, Br minus and I minus. Remember that here fluorine can oxidize all these ions into their respective halogen. Cl minus into Cl2, Br minus into Br2, I minus into I2. For example, if you take 2 KCl plus F2. In KCl, chlorine is in the form of Cl minus. So fluorine comes and occupies its position and replaces the chlorine in the form of the chlorine molecule, so that we get the 2KF plus Cl2. So in the place of KCl, you can take the KBr or Ki also. Similarly, if you take the chlorine, chlorine can oxidize only Br minus into Br2 and I minus into I2. So that here, if you take 2 KBr plus Cl2 gives rise to KCl plus Br2. And similarly with iodide also. Then what about the bromine? Bromine can oxidize only I minus into I2. So that if you take 2 Ki Br2 gives rise to KBr plus I2. So here Cl minus is oxidized to the Cl2, Br minus is oxidized, I minus is also oxidized. The only one that is not oxidized is F minus. Chemically F minus cannot be oxidized. So F minus, conversion of F minus into F2 is impossible using any chemical methods. We can convert F minus into the F2 only by electrolytically. So electrolytically only means using the electrolysis process only, fluoride ion can be oxidized to the fluorine molecule. So these are all places where the lower oxidizing element is replaced by the higher oxidizing element from its compounds. So these are the one non-metal displaces the another non-metal. Let us see the third category, that is the disproportionation reactions. Disproportionation reactions means if an element undergo both oxidation and reduction, then such type of the reactions are called as the disproportionation reactions. For example, let us take H2O2 converts into the H2O plus O2. Let us see the oxidation state. Oxygen oxidation state in H2O2 is -1. Here it is -2. Here it is 0. So same oxygen undergo reduction, -1 to -2 means value decreased. So it's a reduction process. And -1 to the 0 value increased, oxidation. So same element undergo both oxidation as well as the reduction. That's why these are called the disproportionation reactions. If a same element participate both oxidation as well as the reduction. Let us take Cl2 reacts with water, forms HOCl plus HCl. So chlorine oxidation state here is 0. In this chlorine oxidation state is +1. Here chlorine oxidation state is -1. Chlorine oxidation number increased, so oxidation. Chlorine oxidation number decreased, so reduction. Now chlorine participate in the disproportionation reaction. Let us see another reaction, that is bromine reacts with H2O to form HOBr plus HBr. So bromine oxidation state 0 here, here +1, here -1. Bromine is oxidized, here bromine is reduced. So participate in the both oxidation as well as in the reduction reaction, so that we can call this one as a disproportionation reaction. Dear students, I hope you understand this class. If you like this video, please do share it with your friends and do not forget to subscribe the channel. Thank you one and all.